Thank you. Thank you. Tonight, we are going to use evil devices in order to perform direct memory access attacks. My name is Ulf Frisk, and helping me with the demos, I have Peter Norin. Thank you. Today, we are going to bust File Vault open. We are going to totally own macOS, Windows, and Linux by DMA code injection. We're going to dump memory at speeds in excess of 150 megabytes per second. We're going to mount live file systems. We're going to do some live memory forensics. We're going to execute code and spawn system shells. My name is Ulf Frisk. I'm working as a penetration tester primarily with online banking security. I'm employed in the financial sector here in Stockholm, Sweden. I'm a Master of Science in Computer Science and Engineering. And I previously presented my work at DEF CON last year. I did a demo lab there at this year's DEF CON, and I also presented here at SecT last year. And I'm interested in low-level programming and DMA. I need to point out that this is a personal project of mine. My employer is not involved in any way whatsoever. I'm here to present PCI Leech. PCI Leech is the PLX Technologies USB 3380 development board coupled with a custom firmware and a custom software. On the image here, you see the PCI Leech device, or the USB 3380 development board in its mini PCI Express form factor. To your left, you have the PCI Express side, which goes into the target computer, or if you wish to call it the victim computer. Once connected, the USB 3380 chip is able to send DMA reads and writes over PCI Express straight into the main memory of the target computer, read and write to the main memory of the target computer. To the right, you have a USB 3 connector, which allows for a connection to a controlling computer. Once connected, the controlling computer is able to send commands over USB to the USB 3380. It's also able to stream data at very high speeds onto USB 3380, which will then forward it into the main memory of the target computer. We are also able to read the main memory of the target computer this way at speeds in excess of 150 megabytes per second. What's really nice about this piece of hardware is that it requires no drivers at all on the target computer, really. It just works on a hardware level. Unfortunately, it's only capable of 32-bit addressing, which means that we will only be able to read memory below 4 gigs. As we'll see later on, that's not really a problem. This is the same hardware as the NSA playset slot screamer device presented by Joe Fitzpatrick. But what makes all this possible is, of course, PCI Express. PCI Express is a high-speed serial expansion bus, or it's not really a bus in its true sense since it's point-to-point communication. It's packet-based, and PCI Express endpoint devices typically consume between 1 and 16 serial lanes, depending on how much bandwidth a device needs. For example, a graphics card that requires lots of bandwidth consumes 16 serial lanes, while a networking card might consume 1 lane. PCI Express is designed to be hot pluggable. It doesn't mean that hot plug always works. It's designed for it anyway. And it's capable of DMA. And with DMA, we mean that a PCI Express endpoint device is able to read and write the main memory of the computer without passing through a CPU core. Here you have a schematic of PCI Express. You have the PCI Express root complex anchored within the CPU chip. And from the root complex, you have several PCI Express serial lanes, which you can connect endpoint devices to. But you can also connect like PCI Express switches and bridges, which in turn you can connect endpoint devices to. So you can say that PCI Express forms a small device network within the computer. And actually, there is a hardware built in here as well, in all modern hardware anyway, since a few years ago, called an IOMMU. It's a memory management unit for devices, and this allows for the operating system or the firmware to actually protect the computer against evil devices. As we'll see later in the presentation, that's not really the case always anyway. These are all PCI Express form factors. You have the standard PCI Express device to the lower left. You recognize it from the desktop computers and the servers. You have the mini PCI Express form factor, which goes behind the back cover on older laptops, pretty much. You have the Express card form factor that goes into laptops as well. You have Thunderbolt, really common on Macs. And you also have Thunderbolt 3 nowadays, which is often co-bundled with USB-C. And you also have the different M2 key form factors shown up here. And that's newer add-on cards for more modern laptops. And also the M2 key M is really common for NVMe drives. So let's start with a demo. We're going to totally bypass Firewall 2 full disk encryption by connecting an evil device to a Mac's Thunderbolt port. So here we have a Mac. Peter is helping me filming here. We have it connected with the PCI-Leach device here. I'm connecting it to the Thunderbolt port here. And once we connected the PCI-Leach device, you can do this on like a running computer. It needs to be booted. It could be in sleep as well. It can't be like completely shut down, but as long as it's in sleep or if it's locked or something like that, it should be possible to attack it. Just connect the PCI-Leach device and run the PCI-Leach Mac Efi recover command. Now it says, please press Command-Control-Power to reboot the Mac. And let's try to do that. And now we are dumping memory, doing some analysis on the dumped memory that we dumped after the reboot. And we have a password candidate here, which is Donald Duck. You should try that password. And as you can see, the Mac is actually booting. Imagine leaving your Mac in sleep or whatever at your hotel room when you go out for dinner, or if you leave your desk at work at lunchtime, going for lunch or whatever, the cleaning lady might stop by. So what's happening here? When the Mac is starting, Thunderbolt is enabled immediately. Thunderbolt carries PCI Express, which means DMA is possible. But there is no password in memory, so we can't really dump anything that's not there. We need to wait until the user actually inputs the password. Then the password is in memory. Fortunately for the Mac users, Mac OS has been enabling the VTD DMA protections for a really long time, so we can't really dump the memory. Mac OS is secure. But what happens if we reboot the computer? Mac OS is no longer running. The VTD DMA protections are dropped, but the memory contents are still around for a few seconds before it's overwritten with new stuff. And this is plenty of time to dump the memory, do some analysis, and get the Firewall 2 full disk encryption password. And once you're in there, it's the same password as the running user. You probably have access to the cloud services and things like that after that as well. So I reported this to Apple in August last year, and they patched it in December. They co-bundled a major EFI upgrade together with Mac OS 10.12.2. They did not only stop the PCI-Leach DMA attack, but also option ROMs attacks and similar things. VTD is now enabled at very early boot before PCI Express Thunderbolt is started. And Apple has been really awesome at firmware security for quite some time now, and you can really see it in their products now. But what's interesting is that many PC UEFIs are still likely to be vulnerable against DMA attacks. But on the Macs, it's all fixed now. Macs are now totally secure. Apple fixed a few remaining glitches in March this year, and so it should be fixed totally now. But let's continue on to another Mac. Fully patched Mac, and bypass the VTD DMA protections. We're going to unlock the computer. We're going to do some live mounting of the file systems over PCI Express DMA. We're going to do some live memory forensics, not against a dumped file, but against the live memory of the Mac itself. But first, we need to disable the VTD DMA protections of the Mac. Then you need to boot it, like really boot it from scratch. press Command R to go into something called recovery mode. Recovery mode is not password protected by default, even if you enable the firewall to disk encryption. You can get into it. Just fire up a command prompt and type nvram boot args dart equals 0, and the VTD DMA protections of the Mac should now be disabled forever after, or until the user re-enables them again. And the user won't really get any notifications that these ones are disabled. So I prepared a little bit. So the VTD DMA protections have been disabled on this MacBook Pro. And it's a new one with the touch bar, so we need a USB-C to Thunderbolt 3 adapter to old-fashioned Thunderbolt that we used on the MacBook Air earlier on. So let's connect the evil PCI Leech device and load a kernel module. It's really as easy as that. The kernel module is now loaded on the Mac victim here. So let's mount the live file system, do some live memory forensics. So now I mounted the live file system. I also mounted the live RAM as a file in Windows. So what can you do when you have the live RAM as a file, virtual file mapped in Windows? Of course, you can run volatility against it, for example. So let's run volatility against it. I'm going to minimize that movie, I think. And volatility on Windows, it's a little bit slow to start. We'll see that the RAM read will start counting when it's running. But meanwhile, we can go in and check that drive. So if you have the live memory mounted as a file here, you can click into the files folder, and you have the entire Mac OS file system running here, running with kernel level privileges. So you can click into the users folder, for example, and spy on the user's files. And if you wish to copy some files, just right-click and copy whatever. It's as easy as that. Now we see that it's actually counting some bytes here as well. So volatility is actually doing its memory analysis here. And against the live memory on the target computer, we haven't dumped any memory, really. And you see that I'm just running a Mac PS3 command here. So we see the process listing. It's really as easy as that. So we really need to get into the Mac. Of course, when we have access to like this, we could probably get into it in multiple ways. But let's try to unlock the Mac, that is, remove the passphrase requirement. So here is the Mac. I don't really know. I know the password on this one, but we can check that it's not blank anyway. I couldn't log on to that one. So let's try to unlock it. I need to specify the kernel module address as well. And it says status 0 is success. So let's see if we can log on. It's as easy as that. We're in. On Mac OS, PCI Express and Thunderbolt is protected by default with VTD, with the IOMU. It's not possible to run DMA attacks against a running Mac OS system unless we tampered with it previously. But it's possible to disable VTD in recovery mode unless you set something called a firmware password on the Mac. Then you can't boot into recovery mode doing this. This opens up for evil maid type style of attacks. When you visit the Mac one point at a time, reboot it, go into recovery mode, disable the VTD DMA protections. You don't know the firewall password after that one, of course, so you need to wait for the user to actually start the Mac again and boot into it and revisit the computer. But the goal of PCI Leech is really to make DMA attacks made super easy. Just download the software, purchase the hardware, flash the hardware, and start pwning. Mount the target file systems as a network drive in Windows, and even the live memory. Click around, edit files on the target. You can even edit raw disk devices and the live RAM. And there were lots of PCI Express form factors. I mean, just purchase some cheap adapters on eBay. They're really easy to find. There are adapters between all the form factors pretty much, so just purchase some adapters and get going. The most expensive adapter is the Thunderbolt to Express card adapter. But let's own the rest of the operating systems as well. Most computers today, they do have more than 4 gigs of memory, unfortunately for us. But if we can get the kernel module into running kernel, the kernel module is able to access all memory. A kernel module should also be able to execute code. So what we are doing is that we can search for signatures in the lower 4 gigs with DMA, and once we find the correct signature, we can patch into that part of the memory and hijack kernel code execution. Let's continue on to Windows 10. In Windows 10, the kernel is most of the time located at the very top of the memory, which means that we can't reach it with the PCI-Leach device, since it's only capable of reading the lower 4 gigs. It turns out that the page tables and the hardware exception layer HAL is often located below 4 gigs. And especially interesting is the physical address 1000. It's often referenced as the HAL heap, but it's really the low stub, and it's containing some interesting memory structures there. And thanks Alex Ionescu for this awesome research. Anyway, at the 1000 physical address, you can find the base address of the kernel paging table, and the PML4 address, and it's really interesting for us. And you can also find the virtual address of the so-called HAL heap, located at another address here. So we can search that with those two memory contents here. We can search the memory and find some really interesting interrupt pointers that we can overwrite with our addresses to our evil code and hijack the kernel code execution flow that way. So we are going to do a kernel implant on Windows 10. We are going to dump the memory, spawn a system shell, and also unlock the computer. So now we need a little bit of luck as well, because Windows 10 might sometimes hang the computer. So, and by the way, as you can see, I can't really log on to this computer with a blank password here. So let's see if we can load the kernel module. Yeah, we inserted it. And the computer seems to be working still. Yay. So let's spawn a system shell then. It's really as easy as that. Who am I? Your system on that computer then, over PCI Express. And once your system, you can, of course, do pretty much everything. You can disable BitLocker or whatever you wish to do. But that's kind of boring, so let's not do that. Let's mount the live memory and the file system. Like that. And now we are, of course, able to go into Windows Explorer, click around among the files in Windows here. You see the Windows directory, you see the users folders here. Of course, you can click into the user folders and copy everything pretty much over PCI Express. It's really as easy as that. So let's log on to this computer and unlock it as well. As you saw previously, we couldn't log on with a blank password. But let's try to log on with a blank password now. And we're in. Of course, we can also dump the memory to a file. So let's do that. Dumping memory with PCI-Leach is usually pretty fast. It's around 150 megabytes per second. Memory on a computer is not one big chunk of memory, so it's divided in different parts. We have like readable normal memory. We have like memory map PCI Express devices in there, which we can't read on other addresses. We have like unreadable memory, such as system management mode memory. So we need to know where the memory locations are. So we ask the kernel on the running other victim computer where those memory regions are. Those ones are reported back to the PCI-Leach main control program. PCI-Leach main control program is asking the kernel module into the target to read a specific chunk of memory. And since we are asking the kernel module to read that specific chunk of memory, it's able to access this no matter what it is, no matter where it are. And we write it into a memory buffer that is stored below 4 gigs, so the PCLH program is able to read it with normal DMA after that. Yeah, and as you see, we got like 149 megabytes per second here. Sorry for that, but we are running through a USB hub here, so that's why the speed is a little bit lower, unfortunately. So that's it for Windows. We can also use other devices than Windows to attack from. PCLH is running on Linux as well, and it's also running on Android. That means you can run it from an attacker device. From Android, you can use a phone for that. Just purchase an OTG adapter and connect PCLH to the OTG adapter, and you're good to go. And here I have an example of I'm owning Windows 7 over from an Android phone here. Anyway, let's attack Linux as well. Linux is enabling something called kernel address space layer randomization. It randomizes the kernel fully in physical memory, at least since 4.8. And that's a problem for us, since the kernel is likely to be randomized in a part of memory we can't read it above 4 gigs. Fortunately, on Linux system, VTD is often not enabled by default. I mean, it's highly dependent on the distro and things like that, but on some distros, it's not really enabled by default. So we can't reach the kernel directly on most computers. What we can do, we can try to locate a part of the firmware called the Efi Runtime Services and patch that part of the firmware in order to gain code execution and pound the kernel that way. So the Efi Runtime Services is part of UEFI that lingers around after the operating system is started. It provides functionalities such as get and set variables, reset the system, reboot it, and things like that. And it turns out that it's always loaded below 4 gigs. And this has a really nice function dispatcher table with function pointers that we can try to find. It has a really nice known signature, so we can search for it and locate it and overwrite some function pointers in order to gain code execution in UEFI. And so we locate that table, we patch the function pointers, we wait for the runtime services to trigger if Linux calls into them. And we patch the kernel then, and we wait for kernel code execution, and we have success, hopefully at least. So let's do a demo. Let's mount the live file system on Linux and unlock the computer by editing etc shadow. Last year, when I talked here at SecT, I used a lot of command line stuff. I was like pulling the files and pushing it back and things like that. So no more advanced stuff like that this year. Just right-click and edit it. So here we have a Kali Linux computer. Actually, it's a live image here, so you know the password on this one, hopefully. But at least the password is, as you can see, it's not QWERTY anyway. So I can't get into the computer. So let's try to trigger EFI. Get into EFI and get Linux to trigger it. So we're searching for the Efi Runtime Services table. Once we find it, we will patch it. And it says here we need to ask Linux to call into this Efi Runtime Services, and it's often triggered if you like do something on the Linux system, such as switch the user. So let's just press log on as a different user here in Kali. And we have a kernel module loaded at this address. Once we have the kernel module loaded, of course, you know, we can mount the live file system. So let's do that. It's really as easy as that. And once you mounted the live file system, you can go in there, files, in the etc folder. We have a nice file called shadow here. Yeah, like that. Just right-click it, edit with Notepad. And in Linux, you have the default password hash of Tor here in the shadow file. And that's kind of boring. So let's replace it with the hash of QWERTY here. And save that file. And let's see if we can get into this Linux system now with the QWERTY password. And we're in. It's really as easy as that. And even funnier, we can actually edit raw disk devices and things like that in Linux. For example, we can open dev.sdb here. Let's have a look at it in our hex editor here. You see like MS-DOS here at the top and FAT32 and this, yeah, things like that. And we can write to it even and save it in the hex editor, but let's not do that. Let's not destroy our file systems here today. So what can you do in order to protect against evil devices? You can keep your Mac OS up to date to the most recent version, of course, and set a firmware password. You should be totally secure against these kinds of attacks. You can also purchase hardware without any DMA ports, of course. If you do have DMA ports on a PC, I would recommend that you set your BIOS password, lock down your DMA port, and also like pre-boot authentication, for example, BitLocker plus PIN. Of course, the long-term solution is for the hardware vendors and the operating system vendors to start using the IOMMU, the VTD, in order to protect against attacks like this. Microsoft have some really interesting stuff in there as well with their virtualization-based security and their DMA guard that is supposed to be coming in the fall creators update. So what are the use cases for PCLH? I mean, awareness. You need to know that full disk encryption is not always invincible. It's excellent for pen testing and red teaming. I know some red teams that actually love this device that use it all the time. It's excellent for forensics. And also, I would urge you not to do any evil with my tool. So when you leave here today, I want you to know that physical access is still an issue. Please be aware of your potential evil-made attacks, for example, on your Mac. PCLH is really DMA attacks made super easy for everyone to use. It's as easy as I've shown here today. And it's used for good, but I also suspect it may be used for evil. And you will find PCLH on my GitHub, and also catch me on Twitter, of course. I have a blog as well. And also thanks to Inception for some really nice previous work in this area. And also thank you to Alex Ionescu for the low stub research and also some PCLH stability improvements. So thank you. Thank you.
Yes, thank you very much for that. That was really good, and I really loved the live demos, and that actually worked.
Yeah, they worked, all of them, all four of them, yay.
We're just like, I'm holding all the fingers. And as you said, Inception, I used Inception. When you first knew about these attacks, you tried to do them with Inception, but this actually seems so much easier than even working Inception. So.
Yeah, I tried it to make it a little bit easier, to add some new features, and of course get it to run over high-speed PCI Express on more devices as well. So it's
So one of the things that I've been doing, I did some red teaming years and years and years ago when we used Inception. And one of the things that you could do with Inception was to freeze the RAMs from one machine and move them to one, and then dump them via PCIe. Is that still possible? Is that something that you tried?
I guess it should be possible on some systems still, and there are some mitigations put into the most recent PC hardware to actually protect a little bit against attacks like that, but it might work still in some cases.
Okay, interesting. So you're saying that the Mac is more or less patched if you're on the latest level, and I've set actually a pre-boot password? Or
the firmware password, yes. It should be totally secure against my attacks at least. So it's
and on the Windows side?
Yeah, I mean, if you're running BitLocker with PIN and the virtualization-based security with the device guard, it should be pretty secure as well.
Okay, any questions from the audience? Yes, I would guess there was a few. Okay.
Yeah, it will work, but it will dump the encrypted memory, of course, so you can't really make any sense of it.
Yeah, the question was for the stream as well, if you have devices that already have encrypted memory, will the attack works? And yes.
Yeah, but it will dump the encrypted memory, of course, so it's, yeah, it might not work for your scenario, but it's...
And yes?
I have some attacks I patch into vulnerable UEFI, for example, before Windows is starting, and then you're like totally able to totally pwn the Windows loader and get from there. But that's like ongoing research here, so it's might get some news on that one. Unfortunately, not possible if the vendor actually secured their BIOS against VTD, DMA, against DMA attacks.
Any more questions from the audience? But what strikes me with these attacks is the speed that you're getting at as well. It's like, because now it's like, how long do you have to leave your laptop in a hotel room for this to actually be executed? It's like, and that's probably as well.
Yeah, I mean, if you're not patched your Mac since December, it's really like plug it in 30 seconds later, you're like a totally compromised. So it's patch your Mac.
Okay, thank you very much.
Thank you.